Hello, I'm going to talk about the string landscape and the swampland. Quantum field theories without gravity included are well understood. They beautifully describe the interaction of the elementary particles, and we pretty much know what constitutes a consistent quantum field theory as long as we don't have gravity. But when we couple the quantum field theory to gravity, which is equivalent to making the space-time dynamical, the metric dynamical, the naive thing to do is to take the same thing we had, just to include the metric as an extra field and add the Einstein-Hilbert action and integrate also over the metric. However, this approach does not work. And the infinities appearing in Feynman diagrams are incurable. And in fact, the conventional approach to quantizing gravity does not work, as Feynman discovered in the 1960s. The most natural conclusion from this would have been gravity cannot be coupled to quantum field theories. And well, that would be, of course, not acceptable because we do have both quantum mechanics and dynamical gravity in our universe. String theory solves this issue, and the basic idea about it is it replaces the fundamental point particles with string or extended objects, more generally speaking. And this still raises the question, well, does it allow you to consistently couple every quantum field theory, let's say in 4 dimensions, to gravity within the context of string theory? Now, string theory comes with 6 extra dimensions, and in order to come down to 4 dimensions, we need to take these 6 dimensions and compactify it on tiny spaces. And there are many solutions to string equations with these compact extra dimensions. Here's a caricature of them, but anyhow, we can do that, and we get different objects and different particle spectrum depending on what excitations of the string or various membranes or branes of various types we have lead to. So we have a huge number of possibilities for low energy effective field theory in 4 dimensions coupled to gravity arising from string theory. So for example, one compactification might give you the gauge group SU4 with 2 generations. Another one might give you gauge group SU3 times SU5 with another matter representations. And then the question is, well, if you just say, I'm interested in arbitrary quantum field theory with some matter, can you cook up an internal 6-dimensional space such that when you put the strings in this background, you get that quantum field theory? If the answer to this question is yes, then the string theory is not going to teach us much, because basically you just start with quantum field theory, and whoever is interested in constructing the internal geometry, that's just an academic exercise. They might as well just, well, they start with the quantum field theory with gravity as they like. However, it seems that we cannot get arbitrary quantum field theories in this way. Indeed, not only we don't seem to get arbitrary quantum field theory, we seem to only obtain a finite number of quantum field theories from string theory. For example, with maximal amount of supersymmetry in 4 dimensions, which is, if you want to have matter, which is n equals to 4, the rank of the gauge groups we get from string theory is always less than 23. And in particular, the gauge group SUM with m bigger than 23, all of which looks not only consistent, they're among the most beautiful finite theories we know of in 4 dimensions. They are not arising in string theory coupled to gravity in 4 dimensions. Now, they do arise if you're interested in objects which carry these gauge symmetries, but not if you wanted to couple to gravity in 4 dimensions. So the quantum field theories from string theory, which arise as consistent parts of a quantum gravity theory, seem to form a measure 0 among consistent quantum field theories. So it just appears that Feynman was almost right. That is, a generic consistent quantum field theory cannot be consistently coupled to gravity. This raises 2 questions. First of all, does the fact that most quantum field theories do not arise in string theory a deficiency of string theory, or a general conclusion about consistency requirements for coupling of it to quantum gravity? And second, and the evidence is emerging that this is not a deficiency of string theory, but there are subtle reasons for consistency of quantum gravity which demand this. Connections with basic facts of quantum gravity, such as unitarity and quantum consistency of black holes, is what leads us to this conclusion. So then, given this, what are the precise criteria which distinguish a good quantum field theory? By good, I mean the ones which can arise as part of the string landscape coupled to quantum gravity, from bad ones, which we call swampland, which do not arise in consistent quantum gravity theories. This is what we call the Swampland Program, to delineate these conditions. So given compactifications, we get certain quantum field theories in this, among the set of quantum field theories, which is infinitely bigger. So basically, if you consider the space of all quantum field theories as this green region here, essentially every point on it belongs to the swampland. At least that's what we believe. And the ones that do arise from a consistent theory of quantum gravity seem to be a much smaller region, and they seem to be in some particular structures, features which may not look natural from the perspective of the entirety of the quantum field theories, but nevertheless, from the point of view of what is allowed in quantum gravity, seem to be very specific. And hopefully, standard model is one of those points that we call the string landscape, or more generally, the quantum gravity landscape. So some proposed requirements to be in the landscape are the following. These are some of the ones that I'm going to review today. There are many more discussions about these. I'm not going to be complete. I'm just going to give you a flavor of what are some of these conditions that people have studied and proposed. Some of them from many years ago, like no global symmetries that I'm going to talk about briefly, all the way to more recent discussions. And this is a rapidly growing subject as we speak. So these are the conditions I'm going to talk about. The first one is that in a quantum theory of gravity, there are no global symmetries, and the only symmetries are gauge symmetries. Quantum gravity is unique, and this is related to what's called the cobordism conjecture. All gauge charges appear in the spectrum. This is really called the completeness hypothesis. Finite effective range for fields. So if you have scalar fields, the range for them seems to be effectively finite. This is related also to what's called the duality conjecture. The quantum gravity theory admits light higher dimensional objects, like in string theory. String is one-dimensional. It could be like in M theory, it has membrane and so on. Gravity is always the weakest force among all the forces you have. It's called the weak gravity conjecture. And there are restrictions on critical points for potentials which would positive value, and this has cosmological implications, and these are what are called the de Sitter conjectures. So I'm going to review these. Some basic fact about black holes. I remind you that if you fix a charge Q and a mass M, then as long as M is bigger than Q, there's a black hole, the solution to Einstein's equation. The extreme case where M equals to Q can also occur. These are the extremal black holes. Black holes have thermodynamical properties. The Wittgenstein-Hawking showed that to us. And in particular, black holes carry an entropy, and the entropy is 1/4 of the area, where the area is measured in the Planck units. And area is the horizon of A is the area of the horizon of the black hole. So why there are no global symmetries? Well, the explanation of this is relatively simple, at least for U1 global symmetries. Suppose you have a U1 global symmetry of charge Q, and you throw it into a black hole. If you throw it into the black hole, from the outside the black hole, there's no imprint of the fact that the charge was thrown in, because it's not long-range force. There's no gauge field coming out. There's no field coming out, and therefore you cannot distinguish this situation from a situation where the black hole has no global charge, and therefore the black hole decay would continue as if it had no charge, and equal amount of positive and negative global charge come out, and therefore the black hole evaporates to nothing, no net charge, and so therefore you make the charge disappear. In other words, black hole would be a way to mediate any global symmetry charge to be violated. The second one is uniqueness of quantum gravity. And this is a generalization of no global symmetry conjecture. So any consistent quantum gravity can be deformed to any other through a finite action physical process. This is the content of the statement. In the context of the string landscape, this means any compactification of string theory can be continuously deformed to any other with finite action. No global charge to distinguish them. So if you have, for example, one string compactification, there's another one, there's some way to get from one to the other, no matter how much supersymmetry one has or doesn't, from one to the other. There's nothing which prevents you from connecting. There's no super selection sectors in gravity. All the would-be quantum gravities that you obtain are connectable, and quantum gravity is basically a unique theory. This in particular means that if you want to have any different kind of quantum gravity in our universe, then any consistent quantum gravity that could exist could potentially be created inside a bubble in our universe. That's a finite action process. Of course, whether this is a behind the horizon or all that is a different question, but at least in principle, there should be a possibility to create any quantum gravity background that is consistent within our universe, within any given one. The third one I mentioned was that all charges, all gate charges appear in the spectrum. So if you have a U1 gate symmetry, all integral charges can in principle appear, but are these charges in the theory? And without gravity, a priori no reason. This is true. For example, we can have a pure U1 Maxwell theory with no charge states at all. But with gravity, the story changes. And the idea for the case of the U1 is relatively simple. Again, we consider this time a charged black hole of mass m and charge q. We know the entropy of this, the number of states carrying this mass and charge, grows exponentially with the horizon area, e to the a over 4. And suppose we consider black hole of charge q, as long as m is bigger than q, there is such black holes. And suppose you take one of them with charge q plus 1 and another one with charge minus q and collide them. By gate charge conservation, the net object will have charge 1, and therefore we have just proven that arbitrary charge appears in quantum gravity. Before I forget, that argument has been extended to discrete symmetries and higher form symmetries and gate symmetries as well. So this is a general statement. We believe it's a general conjecture true statement about quantum gravity. The next criterion is finite range for fields. This is also called the duality conjecture or distance conjecture. Consider a scalar field phi. Without gravity, we usually have no restriction on its range. For example, phi can go from minus infinity to plus infinity. However, with gravity, it seems that the range of the field for a given effective theory cannot be any bigger than the Planck scale. So the range of the field is less than order 1 in Planck units. This is if you fix the cutoff in your theory. That is what we mean by fixing an effective description. So in particular, if you consider the space of scalar fields phi, in general, you can have more than one, and they appear in the action with some kinetic term. And the kinetic term defines a metric Gij in the field space for phi. So it gives you a notion of distance in the field space for phi. And you can measure distances in field space. And the statement is that the range in which it is, if you fix your cutoff, the range in which that effective description is valid cannot be more than order 1 in Planck units. And what happens if you try to go more than that value? You can go for more than that value, but in fact, your effective field theory description should break down and a dual description should take over. And the mechanism that this happens is through what's called the distance conjecture, that if you go for large distances, there's a tower of light states emerge whose mass goes exponentially with the distance in field space. So you have an infinite tower of particles appearing, and these new states, these constitute the new degrees of freedom of the dual description. The next conjecture for the swampland is that the quantum gravity requires extended objects. So the fact that there must be extended objects in any theory of quantum gravity like string theory is the requirement for any consistent quantum gravity. For example, M theory has membranes, string theory has strings. And there's an argument which connects this to the distance conjecture in the following way. Suppose you start in a quantum gravity in a higher dimension and a compact phi in a circle going down one lower dimension. From the viewpoint of the lower dimensional theory, the radius mode, the dilation mode of the circle, should be viewed as a scalar field, can be viewed as a scalar field. And if you write the corresponding action, you find it goes like 1/2 grad phi squared. And so you could consider in the large distance, indeed, as phi gets very large, it corresponds to large R, and you get a tower of Kaluza-Klein modes. as is expected. So that's consistent with the distance conjecture. It exemplifies that the distance conjecture works. In this case, it's kind of obvious. But it actually also should work if phi is much, much less than 0. And phi much, much less than 0 corresponds to the radius going to 0. So how could, naively, if you have just a quantum field theory with no extended objects, when you take the radius to 0, all the KK modes will freeze out, and you just basically get the dimensional reduction of the theory from higher dimension to lower dimension. So any theory of particles will just automatically truncate to a lower dimensional theory with no tower of states, then no tower of heavy states, and this would be inconsistent with the distance conjecture. But since the duality conjecture says that in any large distance limit of the field, including phi goes to -infinity, there should be life state. This says there must be some other objects that do this, and the only natural mechanism for this to happen is this: if we have extended objects like strings or membranes, which can wrap the extra circle direction, such that because the circle is shrinking now, this wrapping around the circle makes them light, or makes their tension go down, and that will give you a light tower of states. The next as conjecture for the swampland is the weak gravity conjecture, and this conjecture states that gravity is the weakest force among all the forces. This has been observed in string compactification, that among all the forces in a consistent theory of quantum gravity arising by string compactification, the electric force is always the weakest. So in particular, if you have two charged objects of mass m, let's say the same charged object, the electric force, which goes like E squared over R squared in 4 dimension, is stronger repulsion than the gravitational attraction, which goes like M squared over R squared. And in other words, the mass of the constituents of these of the fundamental states of the gate charges is lighter than the corresponding charge. For example, in the context of our universe, this is true. Electron has mass in the Planck units 10 to the minus 23 and electric charge 10 to the minus 1. And this is consistent with this inequality, easily satisfied. But this is also satisfied in all the examples we know in the context of string theory, where the fundamental constituent in this case may not be charge 1 state, but could be charge 2 or 3. Some order 1 charge state might be the light one satisfying such a restriction. And there's a black hole kind of explanation, not a proof of the weak gravity conjecture. And the argument goes as follows. So if you start with the extremal black hole with charge q equals to m, and then if you assume that every black hole can decay, then if the black hole emits a charge, small charge q, the charge goes down to q minus q, but it still should not violate extremality, because m minus m therefore should still be bigger than q minus q if you emit a small q charge, small state of charge qm, small mass m. So for this to be true, together with q equals to m means whatever you emitted must have opposite inequality. That is, the mass of that elementary state that you have emitted should be less than or equal to charge. So in other words, demanding that the black holes should be able to decay would suggest that there should be constituents whose mass is less than or equal to q. And we believe that m equals to q can only be satisfied in supersymmetric examples, BPS states in supersymmetric compactifications, for example. So in other words, this decay of charged states will be an explanation of a heuristic explanation, at least for the weak gravity conjecture. There are many applications of weak gravity conjecture to our universe. For example, if you consider our universe, which is approximately de Sitter space, not necessarily exactly, at least it's quasi de Sitter because it has a positive dark energy and it's not varying or not varying much. So it looks like almost de Sitter. And so if you apply the weak gravity conjecture not to small black holes, if you apply to small black holes, you get the mass of the elementary constituent less than q, but you can also consider the big black holes. And if you consider big black holes, you find that the masses of the elementary states are bigger than the q to the 1/2 times 1/4 of the cosmological constant power. So lambda to the 1/4, in other words. So in our universe, this would be that the mass of the electron is less than 10 to the minus 1, bigger than 10 to the minus 31. And indeed, mass of the electron, which is 10 to the minus 23, lies in this window. So as you can see, it's beginning to be a little bit more restrictive in terms of the range. And then interestingly enough, the lower range is close to the bound for the neutrino. If the neutrino carried any charge, this would have been an explanation of why any charged state cannot have lighter mass than the neutrino. But this is only applies to charged states. It'd be interesting to see if this argument can somehow be extended to provide an explanation for why the mass of the neutrino is close to the lambda to the 1/4. So are there restrictions on critical points of potential when potential is positive, and how flat can it get? So this is an important question to settle this for the applications of the quantum gravity, because, for example, it's an important question for early cosmology in the context of inflation, where we have positive potential and rolling potential for inflaton, and late cosmology, where we have a positive dark energy. So, for example, we could have had a universe like this with a potential which is relatively flat, and the relatively flat region for the potential as a function of scalar field could provide a good setup for an inflation model, and the field settling into the minimum, where the tiny energy could provide an explanation for the value of the dark energy, for instance. So, are these kind of potentials allowed in a quantum theory of gravity? So the difficulty in studying these situations is that whenever you have V positive, you have broken supersymmetry. The only examples for supersymmetric backgrounds are V equal to 0, like Minkowski space, or V negative, like anti-de Sitter space. But positive V always breaks supersymmetry, and when we break supersymmetry, we lose analytic control in the context of string theory. So we have relatively few technical abilities to study these. But there are some cases where you have weak coupling regimes where you can trust these calculations. And so in those regimes, and these corresponds to large distances in field space, where, as I discussed before, some light tower states typically emerge, in those cases, you find that the potential dies off at infinity, goes to 0. And so if you're interested in positive potential, what one finds is that the potential goes like e to the minus some constant times phi in string compactification. And in general string compactification, one gets C's of order 1. So this is the typical situation in string theory, and it's kind of consistent with the distance conjecture, because if you think about the potential as being arising from these light states that are emerging at a large distance in field space, then you get some power of the mass of these states contributing to potential, like m to the power of v or something like that. And so the fact that the potential should go like mass with some power leads to this formula, because mass itself scales as e to the minus a constant times the phi, as a distance conjecture supposes. So, okay, so this is what we learned from string example, that there is a structure. And so, and again, in the string landscape constructions, we are interested in knowing whether or not we can have a metastable de Sitter. For example, could our universe be in a metastable de Sitter or not? But regardless, the fact that at large distance phi, you get a potential going to 0, it means that this, no matter how small the de Sitter is, it is above the 0 value, and therefore any positive energy vacuum should decay. So, so in other words, there is no exactly stable de Sitter. At best, they are metastable. Of course, we are not sure presently within string theory whether or not de Sitter or even metastable de Sitter exists. But if they do, they have to be unstable. So this one I already explained, that the connection between the masses will explain why the V scales with some power of m. So the question is, so this explains the behavior of potential at far distances, but we don't know what's happening in the interior of the scalar field when you go to order 1, less than order 1 in field space from the middle. So in general, there could be various possibilities, like there's no restrictions. And this is possible, but it's a bit bizarre given the very rigid boundary conditions that we have found for large distances in field space for V. The de Sitter conjecture, one conjecture from the de Sitter Swampland suggests that this bound V prime is bigger than constant times V is also true interior, or at least if there's no stable metastable situation, which means that if you have a critical point where V prime is 0, the second derivative is sufficiently negative, so sufficiently unstable. This is called the de Sitter Swampland conjecture. And related to this, there's another conjecture called trans-Planckian censorship conjecture, which suggests that some sub-Planckian modes in an expanding universe can never grow too big to cross the Hubble horizon. So if you start with something length Planck or smaller, the expansion of the universe by a factor of AF over AI cannot make that mode exit the horizon, which is 1/h final. And it's surprisingly, this restriction already explains why you cannot have potentials whose slope is too small. So you can find that V prime over V is bigger than or equal to square root of 2/3, which is consistent with all known string constructions. So swampland conjectures and inflation have an interesting relation. It seems like inflation may not be completely ruled out, but typical scenarios seem at least to be highly fine-tuned. The duality conjecture leads to prediction that we cannot have natural arbitrary large field inflation because we get a tower of light states, and that interferes with inflation. Somehow maybe multi-field may overcome this, but it seems at best inflation is unnatural in the context of string theory. Puzzles of early universe arise after one makes one major assumption, which is at odds with what we have learned in string theory and their dualities. The main assumption in inflation and other attempts to solve the early universe puzzle is that you can use Einstein's equation, perhaps with a few more fields, finite number of them, to describe the space-time all the way back to early times. However, string theory dualities cast doubt on this, because going back to small distances or large temperatures correspond to infinite distances in field space in string theory, and we know that there should be an infinite tower of states arising there, so there must be a dual description. So string theory is teaching us that the early universe cannot be described by our field theory with just a finite dressing up like inflation or inflaton field, but it should have infinitely many additional fields, whatever that is. As far as the present and future, if we assume the de Sitter swampland conjecture, we can only be in a rolling potential situation. And moreover, in a short time, we will roll more than the M Planck units. So the distance of the rolling will be too large, and you get a light tower of states. And the estimated time for this you can do, given our current kind of cosmology. You find this bounded by roughly 30 times the present Hubble scale. You can also use the trans-Planckian censorship conjecture to see what that will give you. And you can estimate that if you have a metastable de Sitter, in that case it's allowed, but you find metastable de Sitter is very short-lived, and the time is again bounded by roughly the Hubble, but there's a log correction to the Hubble scale in this case, which gives you the bound of the order of the 2 trillion years. So let me conclude by saying that swampland conditions can lead to potentially observable consequences for particle physics and cosmology, and almost all quantum field theories are in the swampland. Therefore, fine-tuning, such as hierarchy problem, may end up having different solutions. Severe restrictions on consistent quantum gravity theories arise, as we have learned. These ideas suggest restriction on light matter fields and also on positive energy. And this may explain the coincidence problem of that why the dark energy has anything to do with the Hubble scale energy today. New ideas such as dualities are expected to play a key role for early universe. Thank you.